G'day, my name's Peter Jamieson. I'm the Managing Director of Anditi. We're based in Newcastle, Australia. This presentation outlines the work that Anditi's been doing with the International Road Assessment Program in using remote sensing and automated techniques to star rate the safety of roads globally and help save lives. The presentation formed part of an innovation workshop that I attended in the World Road Congress in Prague in October 2023. IRAP, International Road Assessment Program, has set a target to reduce road deaths by 50% by 2030. About 1.35 million people die on our roads globally each year. It's the leading killer of our next generation, the 5 to 29-year-olds. About 50% of those deaths are vulnerable road users, such as cyclists, pedestrians and motorcyclists. About 90% of the deaths occur in low to middle income countries, placing huge demands on the health resources they've got and many other scarce resources that they have in this space. The cost of road deaths and injury is not well understood, but it's about double the annual spending on infrastructure globally, or about 10 times the annual spend on roads and road maintenance. IRAP's vision is to star rate every road globally. The first part of that is to identify and star rate those roads that carry 75% of traffic. We estimate that to be about 15 million kilometres. If we do analyse that using remote sensing data, such as LiDAR and street level imagery, there's about 30 petabytes of data that need to be worked through. We estimate there's about 45 billion safety attributes that need to be identified and considered in coming up with a star rating in that space. It's a large task. To star rate 15 million kilometres, the roads are broken up into approximately 100 metre segments. So there's about 150 million of those that need to be worked through. 45 million kilometres of line markings and lanes need to be analysed. 60 million intersections and associated attributes, and about 300 million poles and trees. That's about 45 trillion coding decisions, which is about 5.6 million decision days if it's done manually. And when all that's done, it still requires QA, auditing, etc., which is basically going back to the same process all over again. IRAP, the Accelerated Intelligent Road Assessment Program, looks to replace a lot of that manual editing with using automated techniques, which we'll talk about in this next phase. We use a wide range of data sources, including satellite imagery, street level imagery, aerial LiDAR, mobile LiDAR, whatever mapping we can get, OpenStreetMap, etc. In short, we use nearly anything we can get access to that's going to be useful to us. The process we go through to do our star rating involves us firstly ingesting the data, the 30 petabytes that we talked about, from a range of sources. We then need to QA that data because, as we all know, not all data is made equal. Once we've worked out what data we can use, we then need to relate that to the road network that's out there and the 100 metre segments that IRAP uses to code it. We then run that through our road viewer technology, which is a combination of automated and semi-automated techniques, and then we visualize that and work through it. Then we have techniques for actually doing rapid QA of the data, which we'll show you a bit about as well. Output from that is data that is 2D and 3D that we can then use to star rate roads. And from that, we generate the star ratings or assets and work through from that space. Traditionally, star rating's been done using someone sitting in front of a video and then trying to estimate how far poles, gantries, walls, etc. are from the road and which is the closest of those objects to the road as you're going along a 100 metre segment, how wide the lanes are, etc. There's a lot of decisions. Approximately 3,000 decisions need to be made every kilometre to star rate the road. It's a lot of work. The processes we use try and draw in data from as wide a range of sources as you possibly can. So we'll use satellite imagery and aerial imagery. That'll allow us to understand the road corridor and the surrounding context of the road. So where it's dual lane, where there are intersections coming up, etc. in that space. We also use aerial LiDAR. Here you're looking at an enhanced version of aerial LiDAR that pulls out brake lines and features such as roundabouts, curbs, medians, islands, etc. And that all feeds into our overall process. We also utilise off-the-shelf mobile LiDAR that's really been captured to help with navigation mapping, but we'll repurpose it and then basically allows us to pull out most of the features we want. This data has some variability. We've been using survey-grade mobile LiDAR, which gives really dense, good coverage, allows us to actually measure the width of lines accurately, the height of poles, the diameter of poles, how big cracks are in the road, where they occur, etc., etc. But like all data, it needs to be checked. There can always be issues with it. And that checking, particularly of mobile LiDAR, takes a lot of work because you've actually got to visually go through it. So we've developed a technique that allows us to assess that data in near real time. We first get the data and remove all features from it that aren't on the road, such as mobile trucks, cars, etc., etc. We then basically check the data to make sure we've got accurate coverage across the whole area, and then we'll make sure that all the line markings, etc., that we need are in place, and then we can work from it from that point. Once we've done all that, we then start to generate a synthetic or a consistent data set. So on the left, we're looking at a normal 360-degree image. On the right, we're looking at a coloured point cloud. And what we do is combine those two to come up with the best set of consistent data we can for the road system. So what you're looking at now is a mobile LiDAR point cloud, a coloured point cloud, but we removed all the vehicles and all the occlusion so that we can see everything that's in the corridor. And then once we have this sort of data, we're then ready to be able to use automated techniques to go through and extract line markings, etc., in the road system. So this is an example of our automated techniques showing basically where we can pick up poles and line markings, trees, signs, etc., through the whole area. This then becomes input for other systems that we use. We can also use survey-grade mobile LiDAR, much denser, but in this we can actually measure the diameter of everything we want to, know exactly where the line markings are, etc. It's just more expensive to use. From all of that data, we then process it to generate the attributes that we're interested in, such as line markings, poles, walls, etc., and we can drop that data down into a shapefile such as the one you've seen, reducing terabytes of input data down to metabytes, about a 1,000,000-time reduction in the amount of data we need to handle. Once we've done all that, we feed this information into our road viewer inspection system. So on the right-hand side, you'll see all of the attributes, 58 of them, that you need to code for each 100-meter segment of the road for IRAP. We populate this with automated information where we can, and then we can populate it either using the road viewer inspection system or other techniques that I'll take you through. So what that allows us to do is zoom into a 100-meter segment, which is shown in the red box on this area. We can go in and manually check what we've measured automatically. We can go in and cut out a section of that road to investigate it in more detail. And in this instance, we can zoom down onto the road system, level it out, have a good look at what's there, looking at the coloured point cloud. And because of the accuracy of the coloured point cloud, we can measure heights and clearances, etc., etc. We have another level of data that we can use, which is the intensity of return, which gives us indication of where the things like line markings and the road surface are. On top of that, we can jump into in-road viewer and look in the 360-degree street level imagery to understand exactly what's there in great detail. Once we've gone through and coded all that information, we then need to QA it. And as I said before, that QA process in the past has involved someone going through that whole manual coding process all over again to make sure things are real. So what we've done is developed our road coder, which is a system that allows us to pull all the information into one space and update the edits on things. So we can actually jump from one feature to another, such as safety barrier end to safety barrier end, intersections, etc., using this. And we've got full video functionality that allows us to very quickly check through this stuff. We've coupled that to a GIS system, QGIS, and as we move through Road Coder, the QGIS responds in the same way, showing us exactly where it's at, so we can bring in aerial imagery and aerial photography, etc., in that space. And then if we have to, we can jump in and basically check it at street level imagery to make sure that everything's correct and gone through. So over the last 4 years or so, we've developed a whole suite of techniques and tools to allow us to scale at an industrial scale to code or star rate the roads across the world. Now what we need to do is make it happen. Thank you. My name is Peter Jamieson, Managing Director of Anditi.